Hello, our presentation topic is development of sensing and diagnosis technology for Tele-operated CAV. Our supervisor is Professor Hail Kim, and our team name is AIJunior. Our team has developed two key technologies for autonomous vehicles. The first is a diagnostic technology, including an LLM-based system for determining autonomous driving feasibility and MTOD. The second is a sensing technology, specifically the lane keeping assist system. We will introduce each technology in turn.
This project involves developing software to diagnose autonomous driving feasibility, use GPS and camera data, and creating the MTOD system. We use sensor data to classify hardware and software issues. The project aims to advance autonomous driving technology and improve vehicle safety. Programs that we used in this project is as follows. Our system flow involves detecting sensor or camera problems to immediately switch to TOD. If no hardware issues are detected, captures driving video and analyzes it via LLM and assesses whether TOD conversion is necessary. Real-time speed and GNSS data are processed through ROS, and if the car is calculated to have no movement for 10 seconds or maintains a speed of 0, it is considered to be in a stationary state. The code captures driving video and sends them to the LLM model to inquire about the traffic situation and the necessity of switching to TOD. The LLM model responds with a situational analysis and directs either to switch to TOD or maintain autonomous driving with OX signal. To measure the reliability of the LLM models, we applied 3 LLM models to the system and tested them in 5 different traffic scenarios. The 3 LLM models are original GPT-4, a fine-tuned model based on GPT-4, which we will call Traffic Spotter, and Cloud AI. 5 scenarios are, as you can see in the slide. Traffic Spotter outperformed general GPT-4 and Cloud AI with an average accuracy of 96.6%, which is 5% and 2% higher respectively. It also used the fewest tokens at an average of 64, suggesting lower data processing costs. This example shows a case where only Traffic Spotter made the correct decision. This image corresponds to scenario 3, which requires a TOD transition. However, the other 2 models, GPT-4 and Cloud AI, answered X with wrong analysis. And their response formats are not fixed, which can cause software errors when extracting data. To test the TOD transition, we drove an Ioniq 5 on a 50-meter course, pausing briefly at 25 meters. At the end, 2 people were staged to see if our traffic spotter system could detect them and analyze the need for TOD. Image was captured only when the vehicle stopped over 10 seconds near the person, sending data to the LLM model, which then successfully prompts a TOD transition. Lastly, we will explain the implementation of MTOD. Our goal was directly control the vehicle using smartphone and a controller. Although we have not reached the stage of direct control, we have successfully implemented sending signals from the controller's buttons to the server. Lastly, we had a latency test in Songdo campus. Video streaming, brake, and accelerator responses showed 0.5 to 1 second delay, and steering wheel response was nearly instant. In our project's next phase, we aim to reduce latency.
Now, we would like to introduce our next research topic, which is lane keeping assist system. Our main tests were lane detection, curvature calculation, and steering angle calculation. Our ultimate goal was to implement an LCAS for stable driving on covered roads. There are 2 main approaches to lane detection, traditional methods and deep learning-based methods. However, traditional methods struggle with complex road environments and lighting changes. Among deep learning-based methods, we compared Yellow PV2 and ultra-fast lane detection V2. Yellow PV2 demonstrated stable and accurate lane detection in various environments, whereas ultra-fast lane detection V2 showed incorrect detection in some situations. Thus, we chose Yellow PV2 for our lane detection algorithm. Yellow PV2 segments lane lines in the form of a segmentation image. Unlike other detection methods, this segmentation includes some buffer around the lanes. The lane is usually centered in the segmented image by analyzing the segmented mask and transforming it through a bird's-eye view, and then applying a sliding window. We obtain two curves for each lane. Extracting the central line between these curves is a line closer to the actual lane. This approach improved the accuracy of our curvature calculations. Now, let's look at calculating lane curvature using yellow PV2. Accurate curvature calculation is essential for correct steering angles. We calculate curvature for the left and right lanes and average these values for overall lane curvature. This ensures accurate calculations, critical for vehicle stability on curves. Next, let's discuss calculating the steering angle from curvature. This ensures the vehicle follows detected lane accurately. We derive the steering angle from the turn radius, adjusting it with a scaling factor due to lack of exact vehicle parameters. The image illustrates this process, showing how the steering angle is calculated to maintain accurate vehicle tracking. In this slide, we present the algorithm implementation video. The second video shows curvature and steering angle visualization. The third video displays estimated lane curves in a bird's-eye view, and the last video overlays these curves to verify accuracy. We are exploring object detection for lane keeping when lane detection fails. A challenge was the lack of precise vehicle parameters affecting steering angle estimation. Future tests with actual vehicles will address this. Thank you for your attention.